Welcome! In this session, we will explore LeetCode problem number 605, Can Place Flowers. This is a classic array-based problem where we determine if flowers can be planted in a garden according to specific rules. We'll break it down step by step and consider potential approaches. Let's dive in. In this problem, you're given a flower bed represented as an array of integers called flower bed. Each element in the array can either be 0 or 1. A 0 means that the plot is empty and available for planting, while a 1 means that the plot is already occupied by a flower. Your goal is to determine if it's possible to plant n new flowers in the flower bed while following one important rule: no two flowers can be planted in adjacent plots. If it is possible to plant all n flowers without breaking this rule, you need to return true. Otherwise, you return false. The input includes the flower bed array and the integer n, which represents the number of flowers you want to plant. It's worth noting that the size of the flower bed can be quite large, up to 20,000 elements, and n can be as large as 10,000, but it will always be non-negative. The function you write should return a Boolean value, either true or false. A value of true means that it is possible to plant all n flowers in the flower bed without violating the no adjacent flowers rule, while false means it is not possible. For example, consider the input flower bed equals 1, 0, 0, 0, 1, and n equals 1. Here, the flower bed has 5 plots, with flowers already occupying the first and last plots. You can plant one new flower in the empty plot at index 2. Since this doesn't violate the no adjacent flowers rule, the function should return true for this input. After planting the new flower in the example, the flower bed transforms into 1, 0, 1, 0, 1. This updated configuration clearly shows that no two flowers are adjacent, meaning the rule is respected. Therefore, the output is true. Now, let's look at another example. If the input flower bed is still 1, 0, 0, 0, 1, but n is now 2, things change. While you can plant one flower in the empty plot at index 2, planting a second flower anywhere would break the no adjacent flowers rule. Hence, the output in this case would be false. In another scenario, consider the input flower bed equals 0, 0, 1, 0, 0, and n equals 2. Here, the initial flower bed has 5 plots, with a flower already occupying the third plot. You can plant the first flower at index 0 and the second flower at index 4. This ensures that no two flowers are adjacent, as there is at least one empty plot between any two planted flowers. After planting, the flower bed becomes 1, 0, 1, 0, 1, which satisfies the rule. Therefore, the output is true. This example highlights how careful placement can allow for multiple flowers to be planted even in a constrained flower bed. It's important to consider edge cases when solving this problem. For example, if n is 0, you should immediately return true since no flowers need to be planted. If the flower bed contains only 0s, you need to calculate whether there's enough space to plant all n flowers without violating the no adjacent flowers rule. On the other hand, if the flower bed consists entirely of 1s, you should return false unless n is 0, as no additional flowers can be planted. Finally, be mindful of small flower beds with lengths of 1 or 2, as these scenarios could present boundary conditions that need special handling to ensure correctness. To start, let's consider the brute force approach. The idea here is straightforward. We iterate over every position in the flower bed array to determine if we can plant a flower at that specific spot. For a flower to be planted at index I, 3 conditions must be true. First, the plot at flower bed, I, must be empty, meaning it equals 0. Second, the left neighbor, flower bed, I1, must either not exist if we're at the first position or also be empty. Third, the right neighbor, flower bed, I+1, must either not exist if we're at the last position or be empty as well. If all 3 conditions are satisfied, we plant a flower by incrementing our count of planted flowers. This process continues until we've planted the required number of flowers or traversed the entire array. While this approach is simple and intuitive, it comes at a cost. The time complexity in the worst case is n squared, as we may repeatedly check neighboring plots. However, the space complexity is efficient at 1, since no additional data structures are used. This simplicity, though, is offset by inefficiency for larger flower bed arrays, making it less suitable when performance matters. Now, to address the inefficiencies of the brute force approach, we can look at an optimized strategy. This method takes advantage of the sequential nature of the flower bed array to reduce redundant checks. The key insight here is that when we encounter an empty plot, we only need to verify whether the plots immediately before and after it are also suitable for planting. If we can plant a flower, we set flower bed I to 1 and skip the next plot entirely by incrementing the index by 2. Why? Because consecutive flowers are not allowed, so the plot right after a newly planted flower is automatically invalid. The steps are as follows: traverse the array from left to right, check the conditions for planting at each plot, plant a flower if possible, and skip ahead to minimize unnecessary checks. Additionally, if we reach the required number of flowers before the end of the array, we can terminate early, saving further computation. This approach significantly improves efficiency, reducing the time complexity to O(n), as each plot is visited at most once. Like the brute force method, it uses O(1) space since no extra storage is required. This makes it a much better choice for larger inputs, as it avoids the repeated work that slows down the brute force solution. The optimized approach stands out as the best choice due to its balance of efficiency and simplicity. The pivotal realization that planting a flower allows us to skip the next plot drastically reduces the number of checks required, which is why this method achieves an O(n) time complexity. This is especially beneficial for large flower bed arrays, where the brute force approach struggles to scale. There are a couple of key observations that refine this strategy further. First, handling boundary cases such as the start or end of the array simplifies the logic since we treat these edges as special cases. Second, by skipping the next plot after planting, we streamline the process, avoiding unnecessary evaluations. Ultimately, we chose this approach because it delivers the desired results efficiently and with minimal code complexity. While the brute force method might be easier to understand initially, it becomes impractical for larger inputs. The optimized approach strikes the perfect balance between clarity and performance, making it a clear winner for solving this problem effectively. To solve this problem, we are tasked with determining if we can plant n new flowers in a flower bed array without violating the no adjacent flowers rule. The rule states that you cannot plant a flower in a position if either the left or right neighboring plot is already occupied. To begin, the first step is to validate the input. If n is 0, there's no need to plant any flowers, so we can return true immediately. Conversely, if the flower bed array is empty, it's impossible to plant anything, so we return false. Once the input is validated, we initialize two key variables. The first is count, which keeps track of the number of flowers successfully planted. The second is a loop index, I, which we use to iterate through the array. These initial steps ensure our solution is both logical and efficient from the start. Now, we proceed to iterate through the flower bed array to determine where we can plant flowers. For each position, if the current plot is empty, meaning flower bed I equals 0, we then check its neighbors to see if it's eligible for planting. If the position is at the start of the array, we ignore the left neighbor, and if it's at the end, we ignore the right neighbor. For all other positions, both neighbors must be empty for us to plant a flower. If the conditions are met, we plant a flower by setting flower bed I to 1 and increment the count variable. Once a flower is planted, we skip the next index by incrementing I by 2, as planting a flower here automatically makes the next position ineligible. Additionally, if at any point the count reaches or exceeds n, we can return true immediately, avoiding unnecessary computation. Finally, after the loop ends, if we haven't planted enough flowers, we return false. This combination of neighbor checks, in-place updates, and early exits ensures both correctness and efficiency. This approach leverages a greedy strategy, where we plant flowers at the earliest valid positions to maximize the use of available space. Skipping to the next valid index after planting ensures the no adjacency rule is respected without needing additional checks. Let's also consider some important edge cases. In a single plot flower bed, such as 0, planting one flower is possible, so the output would be true. If the flower bed is already fully occupied, like 1, 1, 1, planting any flowers is impossible, so the output is false. In a sparse flower bed, such as 0, 0, 0, planting two flowers is feasible at indices 0 and 2, which results in an output of true. From an efficiency perspective, this algorithm runs in O(n) time since we traverse the array once, and it uses O(1) space as no additional data structures are required. The flower bed array is updated in place, and the count variable keeps track of progress, ensuring minimal memory usage. To further optimize this solution, we make use of early exits and in-place updates. If the count of planted flowers reaches n during the iteration, we terminate the loop immediately, saving unnecessary computation. By modifying the flower bed array directly, we avoid the need for auxiliary space, which ensures the memory footprint remains low. Let's walk through an example to see this in action. Suppose the input is flowerbed equals 1, 0, 0, 0, 1 and n equals 1. We start with count equals 0 and iterate through the array. At index 0, the plot is occupied, so we skip it. At index 1, the plot is empty, but its left neighbor is occupied, so we skip it as well. At index 2, the plot is empty, and both neighbors are also empty, so we plant a flower here, update flowerbed 2 to 1, and increment count to 1. We then skip the next index. The loop ends with count equal to n, so we return true. This example demonstrates how the algorithm efficiently handles real-world scenarios while adhering to the problem's constraints. This Python solution solves the LeetCode problem number 605 can place flowers. The goal is to determine if you can plant n flowers in a flowerbed array without violating the rule that no two flowers can be adjacent. ### explanation. 1. Initialization asterisk. Count is initialized to 0 to keep track of how many flowers we have successfully planted. Length stores the size of the flowerbed array for convenience. 2. Iterate through the flowerbed asterisk. For each index I, check if the current plot, flowerbed, I, is empty, equal to 0. Additionally, ensure that the adjacent plots, if they exist, are also empty. This is done by checking I equals 0 or flowerbed, I1 equals 0, ensures the left neighbor is empty, or doesn't exist if I is 0. I equals length 1 or flowerbed, I plus 1 equals 0, ensures the right neighbor is empty, or doesn't exist if I is the last plot. 3. Plant a flower asterisk. If the current spot satisfies the conditions, a flower is planted by setting flowerbed, I, to 1, and count is increment. 4. Early exit asterisk. If count reaches or exceeds n, the function immediately returns true to indicate that it is possible to plant n flowers. 5. Final check asterisk. If the loop finishes and count is still less than n, the function returns false to indicate that it is not possible to plant n flowers without violating the rules. ### complexity. Time complexity asterisk O(n), where n is the length of the flowerbed array. We traverse the array once. Space complexity asterisk O(1), as we do not use any additional space proportional to the size of the input. This implementation is efficient and handles all edge cases, such as small arrays, length 1 or 2. Cases where n is 0, always return true. Arrays with no empty spots, return false, or fully empty arrays, plant as many flowers as possible. This is the Java implementation for LeetCode problem number 605, can place flowers. The logic mirrors the provided Python solution, with adjustments for Java syntax and type declarations. Key differences include the use of primitive types, int, and the absence of Python-specific features like dynamic lists. The algorithm iterates through the flowerbed, checking if each spot and its neighbors, if applicable, are empty before planting a flower. This ensures that the placement adheres to the problem constraints. To start with our first example, we have a flowerbed represented as 10001, where 1 indicates that a flower is already planted, and 0 indicates an empty spot. We're tasked with determining if we can plant one additional flower, where n equals 1. Initially, we set count to 0 because no flowers have been planted yet, and the length of the flowerbed is 5. Now, examining the flowerbed step by step, at index 0, we see that flowerbed 0 is 1, meaning the spot is occupied, so we skip this position. Moving to index 1, although the spot is empty, flowerbed 1 equals 0, its left neighbor, flowerbed 0, is occupied. Because of this, we cannot plant a flower here either. At this point, the flowerbed remains unchanged, and count is still 0. Next, we examine index 2. Here, flowerbed 2 is 0, which indicates the spot is empty, and both its neighbors, flowerbed 1 and flowerbed 3, are also empty. This means we can safely plant a flower at this position. We update flowerbed 2 to 1 and increment the count to 1. After this step, the flowerbed becomes 10101 and count is now 1. Moving to indices 3 and 4, both positions are skipped since they are either already occupied or have neighbors that prevent planting. At the end of this process, the total number of flowers planted matches our requirement, with count equal to n. Therefore, we return true as the result. In our second example, the flowerbed remains the same as 10001, but this time we need to determine if it's possible to plant 2 flowers, as n is now 2. The count is initialized at 0, and the length of the flowerbed is 5. Looking at the first 2 indices, both are skipped because index 0 is already occupied, and index 1 has a neighbor at index 0 that is occupied. The flowerbed and count remain unchanged at this stage. At index 2, the spot is empty, and both its neighbors, flowerbed 1 and flowerbed 3, are also empty. This allows us to plant a flower here, so we update flowerbed 2 to 1 and increase count to 1. The updated flowerbed becomes 10101 and count is now 1. When we check the remaining indices, from 3 to 4, each position is skipped. Index 3 is skipped because its left neighbor is occupied, and index 4 is skipped because it is already occupied. As a result, the state of the flowerbed remains 10101 and count stays at 1, which is less than the required n of 2. Since we couldn't plant the required number of flowers, we return false for this example. Now, let's move on to a third example. This time, the flowerbed is 00100, and we need to check if we can plant 2 flowers, so n is 2. Once again, we initialize count to 0, and the length of the flowerbed is 5. Looking at index 0 in this new example, the spot is empty, and since there are no left neighbors to consider, we check the right neighbor, flowerbed 1, which is also empty. This allows us to plant a flower at index 0. We update flowerbed 0 to 1 and increment count to 1. The updated flowerbed becomes 10100 and count is now 1. Moving to indices 1 and 2, both positions are skipped. Index 1 is skipped because it has a neighbor at index 0 that is occupied, and index 2 is skipped because it is already occupied. At index 3, the spot is empty, but its left neighbor, flowerbed 2, is occupied, so we cannot plant a flower here either. The flowerbed remains 10100 and count is still 1. Finally, we evaluate index 4. The spot is empty, and both its neighbors are suitable for planting. Flowerbed 3 is empty, and the right boundary beyond index 4 is also considered empty. This means we can plant a flower at index 4. We update flowerbed 4 to 1 and increment count to 2. The updated flowerbed becomes 10101 and count is now 2. At this point, the total number of flowers planted matches the required n, so we return true for this example. This concludes our solution walkthrough, demonstrating how the algorithm evaluates each position step by step to determine whether the required number of flowers can be planted without violating the rules. The time complexity of this solution is O(n), where n represents the length of the flowerbed array. This is because the algorithm involves a single traversal of the array. During this traversal, the for loop visits each position in the flowerbed exactly once, contributing O(n) to the total runtime. At each position, the algorithm performs a few simple checks to determine whether a flower can be planted. These checks involve examining the current spot and its neighbors, which are constant time operations, or O(1). Additionally, if the conditions are met, the algorithm modifies the value of the current position to reflect the placement of a flower, which is also an O(1) operation. Since all these steps are linear in the number of elements and involve only constant work per iteration, the overall time complexity of the algorithm is O(n). The space complexity of this algorithm is O(1), meaning it uses a constant amount of extra memory regardless of the size of the flowerbed input. This is because the algorithm modifies the flowerbed array directly, rather than creating a copy or using additional data structures. The only extra memory used comes from a few scalar variables, such as count, length, and I, which take up a fixed amount of space. Since no other auxiliary structures are introduced, and the memory usage does not grow with the size of the input, the space complexity remains constant at O(1). This makes the solution highly space efficient. To understand the efficiency of this approach, let's compare it to a brute force method. A naive solution would involve generating all possible configurations of flower placements in the flower bed and checking whether the required number of flowers can be planted. However, this would result in an exponential time complexity of O(2 to the power of n, as there are 2 to the power of n possible configurations for a flower bed of size n. Additionally, storing these configurations would require exponential space, making this approach impractical for large inputs. In contrast, the optimized solution avoids this inefficiency by directly checking the planting conditions during a single traversal of the array. This reduces the time complexity to O(n) and the space complexity to O(1), making the algorithm significantly faster and more memory efficient. Now, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best case, if no flowers need to be planted, the algorithm terminates immediately without iterating through the array, resulting in an O(1) time complexity. For the average case, in most practical situations, the algorithm will need to traverse a significant portion of the flower bed to determine if the required number of flowers can be planted. This results in an O(n) complexity. In the worst case, the algorithm will need to inspect every position in the flower bed, such as when the flower bed is densely populated, or when the number of flowers to be planted is large. Here, the complexity is also O(n). Overall, the algorithm maintains efficiency even in the worst-case scenario. Finally, let's confirm the big O complexity mathematically. The algorithm's main loop iterates over the flower bed exactly n times, where n is the size of the array. During each iteration, the algorithm performs a constant amount of work, including checks and updates. This means that the time complexity is the product of O(n) for the loop and O(1) for the operations within each iteration, resulting in O(n) overall. As for space complexity, since the algorithm does not use any additional data structures and only relies on a few scalar variables, the memory usage is constant, or O(1). These analyses confirm that the solution is both time-efficient and space-efficient. When solving this problem, there are several common mistakes to watch out for. The first is not considering edge cases, such as the boundaries of the flower bed. For example, if your flower bed is 0, 0, 1, 0, 0, a naive solution might incorrectly assume it's valid to plant at index 0, but that would violate the spacing rule. Another mistake is overwriting values in the flower bed array without verifying if planting is valid at that position. This can lead to configurations where flowers are planted too close together. Similarly, failing to handle consecutive zeros properly can be a pitfall. For instance, in a flower bed like 0, 1, 0, 0, 0, 1, the zeros between the ones need to be carefully analyzed to respect the spacing rule. Misinterpreting problem constraints is another issue, such as assuming the flower bed has infinite length when it's finite, which can lead to unnecessary complexity. Lastly, inefficient solutions, like iterating over the array multiple times instead of using a single linear pass, can make your code less optimal. Avoiding these mistakes will ensure a robust approach to the problem. To excel in interviews, it's important to focus on a few key insights. Recognizing patterns is essential. This problem often boils down to identifying sections of the flower bed, like blocks of zeros, where flowers can be planted while adhering to the spacing rules. Breaking the problem into smaller subproblems, such as analyzing the zeros between ones, can significantly simplify your thought process. Additionally, communicating edge cases early on is a great way to demonstrate your thoroughness. For example, you might discuss scenarios like 1, 0, 0, 1, 0, 0, 0, or 1, 0, 0, 0, 0, to show that you've accounted for different configurations. Interviewers also value optimal solutions. While a brute force approach might work, being able to describe or implement a single-pass solution with O(n) time complexity will set you apart. Finally, translating problem constraints into code is another skill to highlight. For instance, carefully handling details like the fixed size of the flower bed or the number of flowers to plant can demonstrate your attention to detail and problem-solving ability. This problem shares underlying principles with a few related problems that can help you strengthen your understanding of constraints-based problem-solving. Of course, the core problem here is LeetCode 605, can place flowers, but there are other challenges worth exploring. For example, LeetCode 134 gas station focuses on finding valid positions under specific constraints, which is conceptually similar. LeetCode 763 partition labels involves dividing a sequence into partitions based on certain rules, which mirrors the idea of analyzing blocks of zeros in the flower bed. Lastly, LeetCode 1221 split a string in balanced strings deals with splitting strings based on balance criteria, which can also help you sharpen your skills in handling division and grouping problems. Studying these related problems can deepen your understanding of constraint-based logic and help you approach variations more confidently. There are several approaches to solving the flower placement problem, each with its own trade-offs. The brute force approach involves checking each position in the flower bed to see if a flower can be planted. While this is straightforward to implement, it can be inefficient, with a time complexity of O(n) squared, in certain cases due to redundant checks. A more optimal method is the greedy approach, which uses a single linear scan to find valid positions and stops early once the required number of flowers are planted. This method is efficient with O(n) time complexity but requires careful handling of edge cases. Another option is to simulate the planting process using extra space by creating a copy of the flower bed so the original array remains unmodified. This can be helpful for debugging but uses O(n) additional space, which might not be ideal in an interview. Finally, the two-pointer technique is another efficient option. Here, two pointers are used to identify blocks of zeros between ones and calculate how many flowers can fit. While slightly more complex than the greedy approach, it balances efficiency and precision. Understanding these alternatives allows you to choose the most appropriate solution based on the constraints and goals of the task. Great job! To recap, we solved the can place flowers problem by applying an efficient greedy approach. We reviewed its time and space complexities and discussed key takeaways, such as handling constraints and edge cases. Keep practicing, and don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!